Boundary conditions of electrodynamics. So we know that the Maxwell's equation are del dot D is equal to rho f. So we can write this is the differential form of Gauss's law. So we can integrate this in the volume. So integral the volume integral B del dot d d tau is equal to integral rho f d tau. So we have to multiply this with the d tau and have to integrate for the volume. So when we apply the divergence theorem, this will become closed integral d dot dA is equal to qf, because rho f is charge density, charge per unit volume into volume, you will get the total charge, total free charge qf. So the integral form of Gauss's law in electrodynamics is closed integral d dot dA is equal to qf. So our second equation is del dot B is equal to 0. So when we integrate for the volume, multiply the both sides with the d tau and integrate for the volume. So you will get integral V del dot B d tau is equal to 0. This can be written as closed integral B dot dA is equal to 0. This is the integral form of this del dot B is equal to 0 equation, that is there is no magnetic pole or monopoles exist. So this is its integral form. This is the second equation of Maxwell's in electrodynamics. So this is closed integral B dot dA is equal to 0. This is the second equation. Then the third equation, del cross E is equal to minus dou B by dou T. This is nothing but Faraday's law in differential form. So in order to get the integral form of this equation, we have to multiply both sides with the ds. Then because this is a curl equation, so we multiply both sides with the dA and have to integrate for the surface. So surface integral del cross E dot ds is equal to dou by dou T of integral B dot ds. So this is equal to, using the Stokes theorem, closed integral E dot dl is equal to minus d by dt of integral B dot dA. So this is the integral form of Faraday's law. So the last one, that is the this is the differential form of Ampere's law modified by Maxwell's, that is del cross H is equal to JF plus dou D by dou T. So we have to change this equation into integral form. For that we have to multiply all the terms with the dA and then to integrate. So you will get integral del cross H dA is equal to JF dA plus dou by dou T of integral D dot dA. So this is when we apply the Stokes theorem, this is equal to closed line integral H dot dl is equal to IF plus d by dt of D dot dA. So the first step to derive the boundary condition is to make all the differential equation into integral form. Now we convert Maxwell's differential equations into integral equations. Then we can apply the boundary conditions for the boundaries between two medias. Normally any vector can be split up into two vectors, that is one is parallel to one parallel component and perpendicular component. Here also we will find out the perpendicular component and parallel component of E or D, and also we can calculate the perpendicular component and parallel component of B, or we can write it in terms of H. Okay, so for that, first we will consider Gaussian surface and then we consider the ambient loop. For the equations which is in the surface integral form, so we will get a closed surface form. For that type of equations, we will apply the Gaussian surface or Gaussian pillbox. And for the line integral term, we will apply the ambient loop in order to solve the problems. Actually, boundary condition is how the magnetic field and electric field behaves in the boundary. When the wave travel from one medium to another medium, how this component, its perpendicular component and parallel component of electric field vector and magnetic field vector changes. That is the boundary condition. So first we have to consider the Gauss's equation, that is closed integral d dot dA. D dot dA, d is displacement vector, dot dA is equal to qf enclosed. This is the charge enclosed, free charge enclosed. Okay, so here this is the Gaussian pillbox. We are considering the Gaussian pillbox. So we have to study only the surface phenomenon. So in order to study the surface phenomenon, the thickness of the Gaussian pillbox should be very small. So we can neglect the thickness. Okay. Then then we can study this, how this will behave at the boundary. For that, let us take this equation d dot dA is equal to qf enclosed. So d, there is two surfaces in the upper surface and lower surface. Okay. So in the upper surface, this displacement vector is d1, and in the lower surface the displacement vector is d2. So here thus the closed, when we calculate the closed integral d dot ds, we have to consider the upper surface, lower surface and the side surfaces. We can neglect the contribution from the side of this pillbox because the thickness is very small. Then only we can study the surface phenomenon. Okay. Surface phenomenon means what happened at the boundary. So in order to study what happened at the boundary, the thickness of the pillbox should be very small. So we can, when we do the closed integral d dot dA, this will be d1 dot a minus d2. This is in the upper surface, and minus d2 dot a in the lower surface, because the area vector is always normal to the surface. In the upper surface it is in this direction, and the lower surface the area vector is in the reverse direction, so there comes a minus sign. So d1 dot a minus d2 dot a is equal to sigma f into a. The total charge enclosed the surface include only the surface charge density, because the volume is very small, so we can neglect the volume charge density. We will consider only the surface charge density. So total charge density is equal to sigma f into a. So here a is positive, it points from 2 to 1, and it is negative if it's point from 1 to 2. So here this is negative. The thickness is very small, so the volume contribution of charge density is 0. So this can be written as d1 perpendicular minus d2 perpendicular is equal to rho f. Sorry, not rho, sigma f. Sigma is the surface charge density. So d1 perpendicular minus d2 perpendicular is equal to sigma f. This is the first boundary condition, or we can say that the component of D that is perpendicular to the interface is discontinuous by an amount sigma f. Okay. The same procedure we can apply for the magnetic field also, for the perpendicular component of magnetic field. Here closed integral b dot dA is equal to 0. We know that this equations says that there is no magnetic monopole exist. Similar way, we can consider a Gaussian pillbox with very thin thickness. So we can apply the same case here also. Here, when we look at this equation, we know that the contribution is 0 because there is no source term here. So this equation can be written as b1 dot a minus b2 dot a is equal to 0, or b1 perpendicular minus b2 perpendicular equal to 0. So here this is the equation, b1 perpendicular minus b2 perpendicular equal to 0. That means the perpendicular component of magnetic field is continuous at the surface, or the component of B which is perpendicular to the surface is continuous. It is not discontinuous. So from the first two equations, we studied that the perpendicular component of the component of electric field which is perpendicular to the surface is discontinuous by an amount sigma f, and the component of magnetic field which is perpendicular to the surface or at the boundary is continuous. And the equation number 3 is closed integral E dot dl is equal to minus d by dt of surface integral B dot dA, and closed integral H dot dl is equal to IF plus d by dt of d dot dA. So in these two cases, because this is a line integral, we will consider an Amperian loop. It is Amperian loop. In order to study the boundary conditions, we have to consider this Amperian loop, and the thickness of the Amperian loop is very small. So let us consider the first equation, closed integral E dot dl is equal to minus d by dt of integral B dot dA. We consider a thin Amperian loop since LHS is a line integral. So this is our Amperian loop. Just consider a paper, and there is a small loop which is perpendicular to that paper. This is the upper side of this Amperian loop, and this is the lower side of this Amperian loop. Okay, paper is for example, paper, suppose there is a paper that paper is taken as an example for the boundary between two medias, and above this boundary, a medium is different from the medium which is below the boundary. So this is the boundary, and we consider an Amperian loop of very small thickness. When we calculate the line integral, the first on the upper surface it is E1 dot L, and in the lower surface minus E2 dot L, because when we take this direction as positive direction, this direction is considered to be negative, so that is a negative sign here. So that is equal to minus d by dt of B dl. Okay, but in the limit, as the width of the loop goes to 0, the flux vanishes. So when the thickness is very small, this contribution thickness of we know that the thickness of the Amperian loop is very small, so the contribution from the surface integral become negligible, or we can take it as a 0. So the flux vanishes. So we can write this equation as E1 parallel minus E2 parallel is equal to 0, because this line is parallel to the surface. The line of Amperian loop is parallel to the surface, so we take E1 parallel minus E2 parallel is equal to 0. That means the component of E parallel to the interface are continuous across the boundary. The component of electric field which is parallel to the boundary or parallel to the interface are continuous. And our fourth equation is closed integral h dot dl is equal to if plus d by dt of d dot dA. Since the thickness of the Amperian loop is very small, so thickness should be very small in order to study the boundary conditions. Then only this Amperian loop will explain the boundary of the surface. So its thickness should be very small. So when we consider a very small thickness, the contribution from this term, surface term, will vanish. So we can write on the upper surface it is h1 dot L minus in the lower surface it is h2 dot L, that is equal to the current enclosed by the Amperian loop of very small thickness. IF is the free current passing through the Amperian loop. No volume current density will be contributed in the limit of infinitesimal width, but a surface current can contribute. Okay. Here let us take this is as an Amperian loop. This is in the upper surface, this is lower surface, and boundary is in between these two surfaces, and its thickness is very small. Okay, so this is a surface current density. Surface current density is nothing but the surface current perpendicular to this surface. This is charge per unit length is known as the surface current density, not charge, current per unit length is known as the surface charge density. So this is perpendicular to this Amperian loop. So consider this is a unit vector which is perpendicular to the surface. When we take n cross this L, so n cross L is nothing but the length of this Amperian loop. So in order to find out this direction of the cross product, take your right hand fingers in the direction of n. You ഫസ്റ്റ് നിങ്ങൾ ഫിംഗേഴ്സ് മുകളിലേക്ക് ഡയറക്റ്റ് ചെയ്യുക. ഏത് ക്രോസ് പ്രൊഡക്റ്റിൻ്റെ ഡയറക്ഷൻ കിട്ടാൻ വേണ്ടിയിട്ട് റൈറ്റ് ഹാൻഡിൻ്റെ ഫിംഗേഴ്സ് ഫസ്റ്റ് വെക്ടറിൽ നിന്ന് സെക്കൻഡ് വെക്ടറിൻ്റെ ഡയറക്ഷനിലേക്ക് സ്മോളസ്റ്റ് ആംഗിളിൽ ടേൺ ചെയ്ത് കഴിഞ്ഞാൽ തമ്പ് എന്ന് പറയുന്നത് ആ ക്രോസ് പ്രൊഡക്റ്റിൻ്റെ ഡയറക്ഷൻ തരും. സോ നിങ്ങളുടെ ഫിംഗേഴ്സ് എൻ എന്ന് പറയുന്ന നോർമൽ ഡയറക്ഷനിലേക്ക് വയ്ക്കുക. കറണ്ട് ഫ്ലോ അങ്ങനെയാണെങ്കിൽ ഈ പിക്ചർ അനുസരിച്ച് കറണ്ട് ഫ്ലോ എന്ന് പറയുന്നത് ഈ ഡയറക്ഷനിലേക്കായിരിക്കും. So when you turn the fingers in that direction, that is towards this. Okay, so when you turn like this, അങ്ങനെ കൈ ഫിംഗേഴ്സ് ഇങ്ങനെ ടേൺ ചെയ്ത് കഴിഞ്ഞാൽ നിങ്ങൾക്ക് എന്ത് കിട്ടും? എൻ ക്രോസ് എല്ലിൻ്റെ ഡയറക്ഷൻ കിട്ടും. ഈ എൻ ക്രോസ് എല്ലിൻ്റെ ഡയറക്ഷൻ എന്ന് പറയുന്നത് ഈ ആംപീരിയൻ ലൂപ്പിന് പെർപെൻഡിക്കുലർ ഡയറക്ഷൻ ആയിരിക്കും. ഈ ആംപീരിയൻ ലൂപ്പിൻ്റെ പെർപെൻഡിക്കുലർ ഡയറക്ഷനിലാണ് ഈ സർഫസിലൂടെ കറണ്ട് ഫ്ലോ ഉണ്ടാവുന്നത്. ഈ കെ എഫിൻ്റെ ഡയറക്ഷൻ എന്ന് പറയുന്നത് ഈ ആംപീരിയൻ ലൂപ്പിൻ്റെ പെർപെൻഡിക്കുലർ ഡയറക്ഷനിലായിരിക്കും. അതേ ഡയറക്ഷൻ തന്നെയാണ് നിങ്ങൾക്ക് എൻ ക്രോസ് എൽ ചെയ്താൽ കിട്ടുന്നത്. ഓക്കെ, അങ്ങനെ എൻ ക്രോസ് എൽ ചെയ്യുമ്പോൾ കിട്ടുന്ന ഡയറക്ഷൻ എന്ന് പറയുന്നത് കെ എഫിൻ്റെ ഡയറക്ഷനിലായിരിക്കും. സോ n cap is the unit vector perpendicular to the interface. So n cross L, this is not I, n cross L, length is the Amperian loop, is perpendicular to both n and L and is normal to the Amperian loop, or it is in the direction of Kf, that is surface current density. So we can write this as first equation as H1 and H2 are the value of H above and below the surface. So here on the upper surface it is H1 dot L minus H2 dot L. This is equal to I into F enclosed. So this IF enclosed can be written as Kf is the surface current density, current flowing per unit length. So Kf dot n cross I. This we know that this is a triple product. This can also be written as Kf cross n dot L. So we can substitute H1 dot L minus H2 dot L is equal to Kf cross n dot L. So this L cancelled. You will get the equation. This is parallel component of H1 parallel minus H2 parallel is equal to Kf cross N. So the parallel component of H are discontinuous by an amount proportional to the free surface current density and its direction is Kf cross N. So the parallel component of H are discontinuous by an amount proportional to the free surface current density. So in general, we can write the boundary condition for electrodynamics as d1 perpendicular minus d2 perpendicular is equal to sigma f, or this can be d1 is nothing but epsilon 1 e1 perpendicular plus epsilon 2 e2 perpendicular is equal to sigma f, because d is equal to epsilon e. Similarly, b1 perpendicular minus b2 perpendicular equal to 0 and e1 parallel minus e2 parallel is equal to 0. And also B1 parallel, this equation is H1 parallel minus H2 parallel is equal to Kf cross N. We know that H1 is nothing but B1 parallel minus mu1 minus B2 parallel minus mu2 is equal to Kf cross N. In particular, if there is no free charge or current density at the interface, then if there is no free charge density or current charge density, epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular is equal to 0. B1 perpendicular minus B2 perpendicular equal to 0. E1 parallel minus E2 parallel is equal to 0. Or B1 parallel minus mu1 minus B2 parallel minus mu2 is equal to 0. This is about the boundary conditions in electrodynamics.